Ma basta, poi
Can you guys hear me? Thank you very much for that enthusiastic introduction. I feel like I can't match the energy of this, but that's on me. So this is very much a work in progress, and it's also joint with my collaborator, Willie Rush Lim, whom I met for the first time here in Bindlevo. So let me maybe get started. Do I go to the next slide? Press the... thank you. Okay, so let me maybe describe this family of maps that I care about. So schematically, are there... Okay. Let me maybe describe the family of maps that I care about. So schematically, I want to fix the degree D and also the degree at 0 and infinity, which are going to be the two super attracting fixed points. So at infinity, it's going to be a D infinity to 1 super attractor. At 0, it's going to be a D sub 0 to 1 super attractor. And then there's a free critical point, which I'm going to call 1. That gets mapped to the critical value C. And this is a D to 1 free critical point. So fixing these 3 values, and I'm going to look at the family of all such maps of this form. And the thing that I want to analyze is whether you can say something about the hyperbolic components in a family of maps of this form and whether they're accessible via external rays. So, for example, you can consider the set of cubic rational maps where 0 is of degree 2, infinity is also of degree 2. And the picture on the left is the parameter space of these maps. So the green are the hyperbolic components of infinity. The red are the hyperbolic components of 0, and the black regions are the bounded hyperbolic components. And if you see, there is this sort of like these peanut-shaped regions kind of along the boundary of what looks like, like a deformation of the unit circle. And also for this particular family, you have, if you do the inversion, the external is exactly the same as the internal, but this is not the case in general. The right side is like a zoomed in version of this branch on this left side of this parameter space, just to give you an idea of what it looks like. So things in general look kind of bad. And if you look at the bounded components, basically what I'm asking is the question of when you have external rays that witness, for instance, the cusp or the roots of these components. And I will try to give a partial characterization of when that happens. Any questions about this? Okay, so maybe let me give another example. You can consider degree 5 maps of where the degree of the super attractor 0 is 2, the degree of the super attractor outside is 4, for instance, and this just produces like this extra number of cusps of these components. And you can have like a zoomed in version of that, which is like the zoomed in portion here. And same question about when these bounded components are accessible. Okay. So the bounded hyperbolic components are the components where the free critical point isn't attracted to either 0 or infinity. And that's the question that I have. So to answer this, I'm going to talk about combinatorial surgery, which is the Pilgrim time blowup. And this is a surgery where you take a rational map on the sphere, and you take a set of mark points X, which consists of the post-critical set, and maybe some other marked points. And you also take an arc alpha that has endpoints in X, such that it satisfies the following conditions. On alpha, it's a homeomorphism, and the interior of alpha does not contain any other points in the set of mark points or the critical set. So under these assumptions, you can do a blow up of F to obtain a map G, where the map G has a higher degree than F, and G is going to be combinatorially equivalent in the sense of like it does not have a Thurston obstruction, and there is a map that has that same structure that is a rational map. So this is, maybe let me give an example. Oh, oops. Okay. So so the way that this blow up works is that you have your original space S, you have some sort of arc, and you have the map F on this sphere. And you're going to consider the map G, where G is going to be maybe let me say it like this. So you're going to define the map G as follows. So you take this arc alpha, you cut along this arc alpha, and you glue in a disk. And you're going to define the map G to be equal to F outside of the disk. And on the interior of the disk, G is going to be the map n-fold cover of the sphere. One way to describe that is if you consider the disk itself and you consider it in the upper half plane model, where the arc alpha is going to be the real line after doing the cut. And you consider the map Z maps to Z to the 2n, and that's going to be a degree n cover of the entire sphere. So maybe let me draw something like this. So you basically look at the endpoints of alpha and you cover the entire sphere like that. Any questions about this? Yes. Is the map G continuous? You're going to prescribe it to be continuous on the boundary, right? So like the description outside of the arc is going to be F. And then on the inside of it, it's going to be given by Z goes to Z to the 2n. And you're going to define the boundary to be in the way that it's continuous. Yes. And then the only, all of the other points on this map, you don't introduce any, other new degrees. The only increases in the degrees that you're going to have are going to be at the endpoints of this arc. And you can do a composition of these kinds of blowups to get whatever resulting map that you want. So in general, we're going to blow up this arc where, maybe let me go one by one. Sorry. So, okay. So to give an example of this kind of blow up, consider a quadratic map that's post-critically finite that is an immediate satellite component of the main cardioid. So for instance, consider the basilica. And we're going to do this blow up where we're going to take alpha to be the arc between 0 and the alpha fixed point. and this arc satisfies the blow-up conditions, you're going to cut it, you're going to glue in a disk, and you're going to define the map on the inside to be z goes to z squared. So then the result, you're going to end up getting a degree 3 map. Actually, maybe let me just reuse this diagram, where infinity is going to be 2 to 1, 0 is going to be 2 to 1, and this free critical point is going to be 3 to 1. So this map is going to be in that first parameter space that I showed you. And in fact, oh, hold on. Yeah. This is the blow up of the basilica. So this is in the dynamical plane. The two components are colored based on where those points in those regions end up under the map of the blow up. So for instance, this red region, this is the immediate basin of the new fixed point at 0. This external green region, this is the immediate basin of infinity. And this black bounded component came from that component of the original critical point. So the way that you do this blow up, when you cut this and you glued in the disk, you can imagine that somewhere in this picture, you can draw the sort of disk as this, like this sector here that traces out a bunch of rays and ends up at this point and this point, and it traces out those rays in the F2 component of 0. Any questions about this? Yes.
G. So after you make this, yes, you apply the map F somehow.
So the map G is given by G is defined as F on the outside of the disk, and G is defined as this enfold cover on the inside of the disk. So yeah. So the thing that I didn't actually describe is that this new alpha is going to be the new 0 of this map G. So the endpoint of the arc alpha is going to be the new 0. Yes, it's going to be in the interior of this component here. Yes. Yes. So the disk, you can imagine it. You have the internal rays, like tracing out to this point here, and then tracing out to the point here. Like you're basically gluing in like a sector of like angle 1/3 in the black region.
Mapped to the other component and then coming back. So it's really not invariant. So if you just substitute this by a disk and put z squared, this is kind of invariant, no?
Sorry, I don't really.
Maybe I don't understand. Okay, don't worry, I'll think about it.
Any other questions? Okay. So under this blow up, you get something that's equivalent to a map in this family. And moreover, like you can have external rays. I'm sorry, how do I back? Yeah, you can have external rays of your original map, and under some conditions, the external rays persist. Basically, if the external rays are invariant under isotropy relative to the mark points, and all the arcs of the pre-image of the external rays for that orbit portrait are isotopic relative to X to a unique arc, and vice versa. So under these assumptions, you have external rays for the orbit portrait in this new map that got blown up. Question or comment? Okay. So the result is if you have a post-critically finite unicritical polynomial that is an immediate component from the sort of like the analog of the main cardioid, then under this blow up for this specific arc, you end up getting a map that is accessible at the cusps. And this is accessible for both the super attracting, both the super attractors 0 and infinity of the new map. Any questions? Oh yeah, on this picture, they would just be like these kind of like the peanutty regions on the sort of like main circle. So these components are the ones that are accessible. Any questions? Okay. So you can't do the you can't make the same argument for an arc that has some point in the critical orbit on it, but you can modify the Pilgrim time blow up. I don't know why it's going backwards. Okay, never mind. I figured out how to get to the next slide. Sorry. You can modify the blow up procedure to allow when you have points on the interior of the arc that are in the critical orbit. So under the assumptions where you can take out the assumption that on the interior of the arc there's no point in a critical orbit, and you can do this blow up by just prescribing for each one of those points which side of the disk you'll define it to be on. And you basically have an arc where if you look at those points, let's say this one is xi and this is xj, you're going to embed a disk like this after you make the cut. So you after cutting along alpha, you can glue in a disk like that, and you can still do the same procedure. So here you kind of have to make the your conditions that the external rays for some family of external rays out lambda exists when F inverse of lambda is isotopic relative to X union alpha, like union the interior of alpha. And if you do this procedure, you end up getting that the hyperbolic components of the form. So if you do this blow up with a unicritical map of the form z to the d plus c, where the internal address is like 1 goes to k goes to km. So not something that is an immediate hyperbolic component of like the main cardioid, but something that is an immediate component of that. Then if you do this blow up, the external rays at the critical point persist. And so for these components, the corollary is that because the external rays persist, the external rays for the blown up map G, so the external rays for that map exist at the root. But they don't exist at the cusp. So maybe let me go back to look at some of the examples of these kinds of components when you zoom it in a bit. So if this was a primary component, these components that butt off of it immediately, these are the secondary components. And for these components, the external rays exist at the root, but not at the cusp. So the cusp here is obstructed from infinity. Any questions? Okay, so you can also do this argument for the tertiary components. So if you consider the components that butt off the secondary component, like immediate satellites off the secondary components, then for these components, you have that the rays, the ones that persist are the ones where the internal angle from the previous component to here is of the form 1/n. So like this angle is like 1/2, this one is like 1/3, but the one that's like 2/3 doesn't exist, for instance. So then if you do this blow up, there's the external ray persists at the attracting fixed point of the first return map, which corresponds to this renormalization. But oops. Yeah. Okay, I think. So the point is, if you look at these components, so for the tertiary components, so that would be like this component here and this component here and so forth. So only the ones where your rotation number from the previous component is of the form 1/n. So like this one is a component of the form 1/2, 1/3, and so forth. Only for these ones, you have the rays at the cusp exist. Oh, sorry. The ones should be like this. Yeah, so I think I'm gonna stop here.
Questions, please.
I have a question. So the question is kind of what about the rest? What what about some other internal addresses?
Yes. Oh, sorry. The other ones where it's finitely many components away from the analog of the main cardioid, those ones will not exist. So neither of these will exist. And the reason is when you do this renormalization, so like this first return map, when you do the renormalization, you kind of like swap like the orientation of like the 0 and the alpha. So when you do that, the portion, so like the rays that would be obstructed by the condition of the you know, like which external rays persist, the ones that will be obstructed are the ones that will land on the interior of this disk. So that's why if you allow more than 3 of these kind of this like first return kind of renormalizations, neither of those two endpoints of that segment, or rather both of them, because each time you swapped orientation, so like one of them will not exist.
So since we have time, I'll try to repeat my question and I guess Nuria's as well about the construction. Could you please clarify, for instance, for the basilica, if you keep G equal to F outside the segment, but inside the segment you just glue the disk and do something, then your new map will preserve the disk, but F acts as period 2 map. I mean, it sends the segment alpha 0 somewhere else. This way it's discontinuous, the map G which you are obtaining.
Sorry, I don't understand what you mean. Sorry, from what I understood, the disk is not going to be invariant because it's going to cover the whole sphere, right?
Yeah, the disk is not invariant.
So it's allowed to be map outside of itself.
Imagine the disk. Sorry, I don't know where. Oh. So like if you imagine the disk being like this upper half region of the sphere, like under that map, you're gonna have like n copies of it. So like this sector, for instance, is gonna map to the entire upper half region of the disk. And then this next sector is gonna map to the bottom. And then the next one is gonna map to the top. So you have like an n-fold covering of the sphere.
Want to ask, can people online ask a question? But then please. I don't know if you hear that. This want to ask, please ask a question. I don't hear anything. So thanks, Reila, Zheng again.